a little bit more percentage points for the actual in-class business. Okay? Sorry about that. Memorize formulas? I think basically you need to know what the hat matrix is. H equals, x prime x inverse x prime. You have to be able to maybe invert it 2 by 2 for the graduate students. If I asked you that problem again, just reproduce your work on the graduate problem.
Great.
That wouldn't be too hard.
Some of them are just long.
Yeah. But no, it's more like, do you understand conceptually what's going on? Okay. Do you understand conceptually what, if I ask you in words, what about, if this had happened, what would you have done? Okay? And I'll probably take something right off the test, saying, if this had happened, what would you have done? Okay? Suppose this was the plot of residuals and so on, or whatever. Or this was the F test, or this was SS res and this was SSE. What is the F statistic? You might have to know that kind of stuff. Okay, how to actually compute the F statistic. Or for the lack of fit, for example. Because on the lack of fit analysis, the machine doesn't automatically come up with an F, right? So I can say, well, what would you do? If I gave you these little examples, this is the actual data. You might have to calculate a sample standard deviation by hand or something. On a couple of problems, you bring your calculator, if you want to. But I mean, really simple ones. So you'd have to know how to calculate SSPE, SSLOF, the F statistic. Okay. I give you an F. I'll give you the percentage points in the F table, determine whether there's a significant lack of fit or something. Something like that. Does it make sense?
Yeah.
Because you have to do those by hand on this exam, right? So anything you have to do by hand, you must know how to do. Okay.
As an open book, or can we make a group sheet?
Yeah, I might as well make it open book. It doesn't much matter. I give you a certain amount of time.
I remember how to do lack of fit, but I always forget what the degrees of freedom are.
Okay. Well, we can work on that. Okay. Degrees of freedom.
I remember one's the multiplicity.
How do you calculate degrees of freedom? Degrees of freedom. So, for example, so some of these conceptual things I think we're going to have to work on. Degrees of freedom. Because it's getting a little bit too applied at this point. Now, what is the degree of freedom? If I have, so I think, so for example, in that catapult data, you could have done a lack of fit test, right?
Right.
And was it asked for? It wasn't asked for in that problem. But how would you have done it? Catapult data. 511.
So first thing we would have done was had to find SSH.
I don't even know how to spell catapult. How do you spell catapult?
That's right.
Is it? Okay. 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 So here was the actual, what you had was you had x1, x2, x3, x4. Degrees of freedom for SSPE, pure error. Okay. And SSLOF. Okay. What you had was x1, x2, x3, x4, and they were each tuple that was given in the problem was distinct. Each x tuple was distinct. There weren't any as it showed, but not quite, because actually it appeared 3 times. In other words, apparently it was distinct, but actually not, because of the way the data was given. It was given as y was equal to 28.0, 27.1, 26.2. So there are actually 3 observations at each input. Okay. So this is a single input. Okay. All the x is the same. Okay. That happened here, it happened here, and it happened here. So what you get is an estimate. So what you get is an estimate of pure error. What you know is that these y values are modeled as mu sub x as a vector. All right, -1, -1, -1, -1, plus error. Okay? Whatever the mean is, and we can model it as a linear combination of the x's, right? Beta 0 plus beta 1, x1 plus beta 2, x2 plus beta 3, x3 plus beta 4, x4. We can say that. But this is mu sub minus 1, minus 1, minus 1, minus 1 in this particular case. So what you can do, therefore, is where the error has variance sigma squared. So you're going to get an S1 is sigma squared, right? Or 2 times sigma squared. What you have is that summation y minus y bar, yi minus y bar, yix, I think we called it. Okay? Minus y bar sub x. Okay? Squared. I goes from 1 to n sub x. The number of times it was repeated, in this case, is 3. Right? This will give you, this will be a component of SSPE, one of the pieces. And how many degrees of freedom is contributed by this? Degrees of freedom contributed by this piece is nx minus 1. Remember I always said you've got 3 y's, that's 3 degrees of freedom. But because you're actually don't have 3 degrees of freedom in this sum of squares. Because the differences you're adding here after squaring, okay, actually when you added them without squaring, come out to 0. So in other words, these 3 vectors, these 3 random variables are not linearly independent, okay, not independent. So what do I mean here? What I mean here is what is the mean of these 3? This is quite simple, right? The mean is actually 27.1, isn't it? Mm-hmm. Okay, so this is 28 minus 27.1 squared plus 27.1 minus 27.1 squared plus 26.2 minus 27.1 squared equals 0.9 squared plus 0.9 squared plus, and then there's a 0 squared, equals 1.62. Okay. Now the actual variance, if you remember this, was not 1.62. The actual variance estimate, the S squared, for this x was equal to 1.62 divided by 3 minus 1 equals 0.81. That was the estimate of the variance. Okay. But we don't actually, we don't divide the sum of squares by its degrees of freedom when we're contributing, making the total contribution to SSPE. Because what we do, we pool sums of squares from each of the different input x. All right? So you're pooling sums of squares. So how many different inputs were there? There were 8 different inputs. You got 2 degrees of freedom from each one. So how many?
16.
There were 16 degrees of freedom for SSPE, therefore.
And we can say that as the summation from, say, j equals 1 to L of n sub j minus 1. So it's the
inputs, each repeated 3 times. 3 times. So nx equals 3 for every vector x. Okay, so then for nx minus 1, sum over all x possibilities equals 8 times 2 equals 16. Right? There were 8 different x's. 16 degrees of freedom for SSPE. We can actually go ahead and calculate the lack of fit statistic. Should we do that?
Yeah.
For this multiple regression, since we never did it for a multiple regression problem in class, let's just go ahead and look at this website for problem 511. I put a little bit more work on 511 and put it in there. Turns out that the whole weighted least squares thing was pretty much...
Didn't add anything to it?
Oh, shoot, I just did it the wrong way. I want to close that, right? Okay, what happened? How do I get out of there? I'll just go ahead and save it on the desktop. Since I did it the wrong way. Forgot how to do it already. Okay. All right. So is it on the desktop now? I guess so. Yeah, it looks like. No, it's not. That's not the right one.
What is that now?
Now it should be here. Okay, here we go. All right, so here was oh, thanks for turning off the light. That was quick. Okay, here is the data from problem 511. And all I'm looking at is just the original x1, x2, x3, x4. Here were some other higher order interactions that I introduced for my own use, and we can refer to later. But what I'm looking at is just, here's the original data. The y value, where did I stick it? I think I put it way over somewhere else. AH with the y values. Okay. And these are the y hats, I believe, from just the original simple linear regression. Multiple regression on x1, x2, x3, and x4. Okay. And so what did I have here? And here was the multiple regression x1, x2, x3, x4. The total residual sum of squares was 8863. Okay. So our SS res was 8863. Okay? Multiple linear regression of y on x1, x2, x3, and x4 with intercept gave SS res equal 8863. What's SS pure error equal to? And this has, how many degrees of freedom did that have? There were 5 parameters, right? Beta 0 through beta 4. Therefore, how many degrees of freedom? 24 minus 5 is 19 degrees of freedom. That's how you count degrees of freedom for SS res. You just take the total number of degrees of freedom, number of y values, subtract the number of parameters estimated. So that's 19. Of course, it's told you right here on the sheet, but you have to know that. Now, okay. So my estimate for sigma squared is 466, dividing that. Okay. So MS res, just put that in there, is equal to 8863 divided by 19 equals 466. Okay. What's SSPE? Then I'd have to multiply all these S squareds by 2, right? Because let's go back up to those. Remember, we had calculated all these sample variances and what the here the sample variances are, 0.81 and so on. Now all I have to do is multiply them by 2 and add them, and I get SSPE. Does everybody follow that? Multiply these sample variances. What's the formula for that? There's a variance AH2 to AJ2. It was these 3 things. That's AH2 to AJ2. Okay, I'm taking the variance sample. I'm taking the actual population variance. No, I'm taking the sample variance. That's the sample variance. Another way to write it is standard deviation squared. Okay, shall I write this one more time? Let's change it. You're good? Okay. That's the sample variance, what I just calculated over there by hand. But that means I've divided by 3 minus 1. There's 3 y's. I take the sum of the squared deviations from the sample mean, which is 27.1. There's the sample mean, 27.1. Right? Take the sum of squared deviations from 27.1 and I divided by 3 minus 1. That gave me the sample variance. So since I'm dividing by 3 minus 1 in all of these cases, because there's exactly 3 repeats right? The 3 repeated y values for each input, x, right? X is a vector, x1, x2, x3, x4. Right? Then to get to SSPE, I'm just going to multiply all those denominators out just to get for SSPE, I'm pooling sums of squares. So that will be equal, therefore, to what I'm doing here. Equal to twice times the sum of all those, right? You should just put zeros with this blanks, I believe, so that should be okay. That looks about right. How much was it? It was 3.5, 4.4, 5, 6, 6.8, and about 7 and something. Okay? Now multiply it by 2. Okay, so the 14.56. Yeah, so if I had used VARP, then it would have given me divide the 1.62 by 3. It would give me a 0.54 or something. 0.54 instead of the 0.81. Okay. But the SSPE cannot be confused. That's the pooled sum over all x, the inputs, the sum over the yix minus y bar sub x squared. I goes from 1 to n sub x. Okay, and the number is agreed, and that's going to be this is estimate. Okay, and then SSPE divided by the sum of the nx minus 1s. Okay, is an estimate. It estimates sigma squared. Is a pure estimate of sigma squared. Okay, so if there really is a common variance, of course, in this problem the assumption was, maybe there wasn't an equal variance, but let's pretend there was. Okay, this would be a pure estimate of sigma squared. Okay, so there could be an inadequacy because of the model not holding, but this is just an example of how to actually do it. Okay, assuming that there really was a common variance, assuming the common variance holds, assuming there is a common variance. That is, variance epsilon I x equals sigma squared for all I for all x. Okay?
For your SSPE, isn't that supposed to be times 2?
Well, this is the total sum of squares. So what that is, if this is in our case, it's equal to twice the summation of the SI squareds. Okay? Or SX squareds, we could call it, but that's bad notation. SI squared, I goes from 1 to 8 in our example. Okay? For example, 511. Problem 511. Okay? Because SI squared is really this inner sum of squares divided by 2. Okay? So to get SSP, I had to take the SI squared multiplied by 2 to get the sum of squared deviations. You see what I'm doing, the multiplying by 2, Bob? In other words, if I was actually calculating SSP, which I started over here, I would start with the 1.62, then I would have added on, the next number, which is 5.6. All right? Okay. We had calculated the SI squareds for a different reason, all right, in this problem, because we want to look at weighted least squares for this problem, which turned out to be kind of a bust. That's all. It was complicated. You had to start studying the log of the variance or something versus all 3 x's, or all 4 x's, okay, to get anything where decent, okay, for the model of the variances. You had to do a transformation, another log transformation. All right, it was way too much work that was really, that I really wanted you to work on that. I just wanted you to know how to do weighted least squares. I want to see the square root of W column, the square root of W times X, and all that stuff. Okay? I think it's, did I ask you a weighted, I didn't ask you a weighted least squares because that was not in chapters 2 through 4. Was it? Oh, yeah, I guess it was in chapter 4. But I didn't ask you on the exam, so we'll save it for later. So that's SSPE, 14.56. So what I have is that's just a little tiny piece of SS-res, right? So therefore, SSLOF is equal to SS-res. What you have is the total sum, the 19 degrees of freedom. This is the big sum of squares. Plus SSLOF. What I said was that these, I said PE. These are statistically independent.
SS-res equals on the right-hand side.
Jeez, I can't get it right. Yeah, I was going to subtract probably, but now I'm going to do it this way. Okay. So here it is. This is the big sum of squares, 19 degrees of freedom. This has 16 degrees of freedom, but it still only adds up to 14 and a half. Okay. So therefore, obviously our model is not adequate. This multiple linear regression model is not adequate. Either that or this assumption about there being a common variance is not true. Okay. But in order to do the lack of fit, we have to assume that there is a common variance. That's the theory. All right? Otherwise, this doesn't work out as independent pieces and so on and so forth. Okay? So then all you do is you add the degrees of freedom must add 19. This is degrees of freedom must add. This has 19 degrees of freedom. It has 16 degrees of freedom. Therefore, SSLOF has the other degrees of freedom, which is 3. Because degrees of freedom must add. Okay? And SSLOF is trivial to get because we just have to subtract again, and then the actual values were 8863. This was 14 point. I guess I could put the decimal points in instead of 8863. It was 8863.18. The SSPE was we calculated 14.56. Okay, and therefore SSLOF is this other 8,849 and so on stuff. Okay, so what's your F statistic now? Your F. So this is what's SSPE divided by its degrees of freedom is the actual pure error estimate for sigma squared. So your F statistic is always a quotient of two variance estimates. And so I have my pure variance estimate, so that's going to really be my sigma squared downstairs, so to speak. That's your 14.56 divided by 16. So according to this, the variance is only 1. Okay? The actual sigma squared is roughly about 1, 14.56 divided by 16. Whereas in your SSLOF estimate of variance, which can be biased if the model doesn't fit. That's the whole point. It'll be biased. SSLOF will be, after we divide by its degrees of freedom, we'll have a bias for sigma squared, the pure error, the pure sigma squared, so to speak. Okay? So that's in the numerator. Okay? Yes?
Alright, so I see how you get 3 there. The degrees of freedom have to add up.
Yeah.
But in the book on page 160 for your F test, it takes SSLOF and divides by M minus 2, where
Okay, but that's only for the simple linear regression. It should be M minus P in general.
M minus P. Okay, cool. That makes sense.
That's a correction.
I get that.
Okay. I mentioned that in class once, but I guess you didn't correct it then. So this comes out to be what? Nearly 3,000. Okay, a humongous F statistic of 3 and 16 numerator and denominator degrees of freedom. So the F has okay. So what would I actually calculate as the percentage point here?
0.
Well, yeah, but Are you following? In other words, if I wanted to see if I rejected the null hypothesis at level alpha equal 0.05, I would go to a table at the back of the book. Percentage points of the F distribution, and look up the critical point for the test. And I'd look, let's say, at alpha equal 0.05. And what would I actually look for there in this table? It's page 559 and 558. Actually, I'll get it from page 558. The number of degrees of freedom for the numerator is 3. The number of degrees of freedom for the denominator is 16. So you look down the column to 16, that's the denominator degrees of freedom. Look over, well, you look down the side of the page. So I'm getting 3.24 is the critical F. All right, as long as this F ratio is bigger than 3.24, reject the null hypothesis of no lack of fit. All right, so F, so 0.05, 316 equals 3.24. If this F is bigger than that number, this F ratio, which is roughly 3,000, okay, here, okay, if this F ratio is bigger than that, which it clearly is, then I reject the null hypothesis, no lack of fit. Okay, so H naught is no lack of fit. Okay, and so we're going to reject H naught.
Can you repeat that again? You said 3.4.
3.24.
24 is smaller than.
No, if this when F is big. Okay, what's the theory? This is unbiased for sigma squared. If my model fits, everything's perfect, this will also be unbiased for sigma squared, this top. And I'll get a ratio of sigma squared, it'll be roughly about 1. Okay? Be middling value. Even when they are both, since they're independent, even if the model is perfect, it's still possible with 5% chance that I'll get an F ratio that's bigger than 3.24 just out of the blue kind of a thing. Okay? Because they're not, this one might come out a half, this would come out 3 halves. Okay? And you get an F ratio of 3. What are you going to do? Okay? So that'll happen. Okay? But if I get a number, but I'm saying, well, if I get a number bigger than 3, then, that shouldn't happen out of the blue, even when the model is fitting. Okay? So I'll reject the null hypothesis, no lack of fit. Because the fact is, if there is a lack of fit, then this thing will have a bias, positive bias. The numerator will have a positive bias for sigma squared. So I have something, sigma squared in the bottom, something bigger than sigma squared on top. In this case, much, much bigger. Okay? So then you just say, okay, there's a lack of fit. It's not a small lack of fit, it's a big lack of fit. Okay? This under the assumption that there was a common variance, error variance, sigma squared, okay, which was somewhat up for grabs in this problem, let's say. So the lack of fit test does require this assumption, okay.
Are we going to generalize the lack of fit test where we don't meet that assumption? Or?
No.
Okay.
Because, well, you could try to transform to it, then still do a lack of fit. That would be the basic method. Try to transform to constant variance.
Which is what theoretically we did.
What you're trying to do, with this weighted least squares, then go ahead and test lack of fit. If you could have gotten the weighted least squares thing to work, okay? But it didn't work out that easily. Okay? I mean, you could play with the data and try to but you know you're going to get a lack of fit here anyway for just a multiple linear regression model. It's not the right model. You wanted some interaction terms. In fact, I think I showed here that, let's see, where'd the sheet go? You can just tell if you play around with this example enough, you're not going to get anything like that. Here's the residuals I got. They look kind of like a pattern to them, unfortunately. I'm not sure what to make out of that. There are the residuals if I use an interactive model, no weighting. Okay? That's kind of bizarre looking residuals.
Well, it's just your groups, pretty much, isn't it?
Yeah, I guess they are. They're just the groups. Yeah. So it's showing this still. Yeah, that's probably what it's showing. It's showing this still. Is that right? Yeah, so that means I must be fitting y bar completely. Is that possible? Let's see. There are 8 y bars. I don't have 8 parameters in this model, though. Okay? Let's see about that. How many parameters? 1, 2, 3, 4, 5, 6, 7. I have 7 parameters in this model. So I'm still catching all the groups even with only 7 parameters. Okay? So in other words, I still have plenty of degrees of freedom left for error. But yeah, I would be catching, if I had 8 parameters, then I'd just be catching y bar, for my, so I'd just be catching the group. So I'm doing a little bit better than that. So now you'd want to sort of throw one of these away too. I guess you don't need x4 in here. You might even get away without x2. Okay? Throw a couple more things away and see if you get something interesting. Yeah, so I'm still not finished with this problem. So it was kind of an interesting problem. If you look at the sheet, you'll see that I did do the regress the log of the variance on x1, x2, x3. You had to actually, and x4, you actually had to fit a transformation of a multiple regression of the variance on all the regressors, x1, x2, x3, x4. That's what they wanted you to do. Try to fix it up. Then redo weighted least squares. So we can do that. If we want to do weighted least squares here, we'll take these variances and this was the original weighted least squares, I think, up there. But here, what I did is I took all these. I took the SI squared and take the log of SI. Okay? And regressed. And did that. Residuals are regression of sample variance on x1, x2, x3. Should have been x3, x4, catapult data, and it's misspelled catapult. But here's the regression of log sample variance on x1, x2, x3, x4. Okay? So I can look at that. Okay? It looks like the variance isn't variance isn't constant when I just do the sample variance on x1, x2, x3, and x4 versus here predicted variance and there's the residual. Okay, so then I said, okay, you could take a square root or something more drastic like the log. All right, let's try to make the variance constant in the residuals. So I took the log. The square root didn't seem to be strong enough, so I took the log. Then what you can do is if you want to estimate the variance, and you have to take you take these predicted values and then take the exponential back again. Okay? And I'm not sure. Let's see. Is that what I did? That would be the log of the variance. I think I took log of the sample variance, so then I'd have to exponentiate them. And I forgot where I did that. Actually, back here, maybe somewhere. Is this it? Oh, predicted. Yeah, here it is. Exponential the predicted log. SI. I guess I should have put log SI squared. I can't remember if I took the log of SI or the log of SI squared. That would make a difference as to whether I got these numbers squared or not. So if I actually squared each of these might have worked out a little bit better. I can't remember whether that was supposed to be right or not. So I might have still an error in this sheet. But that factor of 2, right? When you take the log of SI squared, you get a 2 coming down. That won't affect how the residuals look.
But it will affect.
But it will affect my prediction of the variance.
Wouldn't all of them be off by a factor of 2, and with your weighting maybe?
No, a factor of a square, though.
Oh, by a factor of a square. No.
By a factor of a square. So these 0.4s will go down to what I want it to be, about 0.2, right? Because remember, the variance was about 0.2 in those last 2 places. And this 1.4 will go up to the 2.8. That would be good, right? So this 1.25 will still be too big and so on, but I'm not sure whether this is the right thing. Anyway, they don't smooth that. They're not that close to the actual variances. It's hard to fit. Here I've got, what, 4 parameters? 5 parameters. beta 0, beta 1, beta 2, beta 3, and beta 4, and it still can't fit those variances. Okay? There's only 8 different variances. So it's still not a very good fit. Assuming that I didn't make an error there with a factor of 2. Okay? You play with it yourself if you want to, this problem. It's got some interesting aspects to it. You don't have enough, you don't have the full factorial experiment. In other words, we didn't consider every level of each variable, -1 and 1 for each variable. These levels are coded, so CODED. So x takes values -1 or 1, x low or x high. Okay? And so a full factorial experiment where you take each variable and put it at the 2 levels, or 3 levels if that's what the variable had, low, medium, high. Okay? Here we just had low and high. And you put all possible combinations. Then you'd get 2 times 2 times 2 times 2 different inputs, right? In the 2-valued case. So you'd get 16 different vectors x. Here we only had half the full factorial. We only had 8. So there wasn't that. It was kind of hard to do this problem, okay, without all those. You couldn't bring in the interaction so easily because you had to be careful how many parameters you had. Right? You couldn't load it up with 7 or 8 parameters because then you just get the y bars back. That's not so good. Right? You're not getting an actual idea of what the function is that predicts the distance of the catapult through whatever it was throwing. Okay? All right. So there was a kind of a problem with the not having the full factorial design there in this problem. But it was still interesting. I think the author was getting after this log transformation on the variance. That was my final conclusion. Okay? Okay.
Irrelevant sum was a bad problem.
It was kind of a bad problem. I thought it looked like it was going to be a good problem. And I'd never assigned it before, so I apologize. But sometimes you can get bad problems in this subject. I usually try to, check them ahead of time. I think 90% of your problems were checked, but this one I had never checked. It looked like a good problem. The guy was feeding explanation points in the, in the part C and all that stuff. This must be a good problem. Oh, it wasn't. Okay. Maybe the exclamation point was warning. Okay. Okay, the one the author was frustrated with. Okay, so other comments about this? How do you calculate SSLOF and whatnot? The theory with that? Okay.
So you wanted us to redo the problem?
No, I'm not going to. No, we're just going to skip this. I'll ask you for another weighted least squares or something later. Yeah, we'll put you on the final. On the final we can have a practice problems, and I'll just give you a slew of not a slew, but some practice problems, and then we'll ask questions about these problems, okay, and some other questions that I'll also prompt you with a help sheet or something. Is that okay? I'll give you a sheet, okay, a week from today. Okay.
So there's going to be no take-home question at the final?
You will be taking it home. Like I said, I'll give you problems on that sheet. Do these problems, and I'll ask you about them. If this experiment works out where I'm going to ask you about things on Thursday, what can I say? Be familiar with those problems. Okay? Take them home, and whether I actually, and you can turn them in with your final. I can look at them and see, what you were doing.
In case we did it wrong.
Yeah, that would be a good thing. So to check your work and so on. How's that sound?
So it's basically going to be like we're doing the take-home portion.
Yeah, except that I might add a piece of theory because I have now at least 5.5 lectures left. Okay, to add a piece of theory. So I think I was going to throw in this distributional theory. That's one of the appendices. Just because we've been talking about it so much, and it's my favorite piece. Okay, I might just throw that in. Because I think we actually have enough time here. Otherwise, we're going to get off in Chapter 13, and where you need a lot more computing power and stuff like that. So since we're going to minimize the amount of computing from now on, we'll still be using the homework to illustrate how things go on, but I want you to understand conceptually what the heck you are computing why are all these computations working? The residual stuff, well, that's not so bad, right? So there is a certain amount of just plug and chug, and we need to know what models it is and count the number of parameters and so on. There will still be that part of it. Okay? There's still a lot of conceptual, and then the probability part, the F statistics and so on, I'm going to push just a little bit on that. Okay? See if we can understand what's going on there. Okay? All right. Let's skip this problem now. Let's go back to a different problem. Let's go back and go back to Chapter 6 was about measures of influence, right? Which one was it? Can't remember what all the chapters are anymore. They're going so fast. It is a whirlwind course in the summer. I apologize for that. That, I'm not going to be able to test Chapter 6. Except for saying, unless I gave you a sheet saying, here's what it looked like. Okay? Here's all the columns of HII, blah, 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 which I could do and say, which ones are the influential ones and so on. What would you do and so on and so forth. Just say, read this sheet. Interpret this sheet. You understand what I'm saying? I'm not going to ask you to calculate HII, RITI, Cook's D, and all that stuff. I might just give you a sheet and say, what happened? That's how I could test you on Chapter 6. Study the data from this output. It might have been one of the problems you actually already did, and you actually do. And so I'll just give you the output sheet, the correct answer. Okay, you can tell me, you interpret it. That sound reasonable? I mean, that doesn't sound too bad to me. Already studied the problem. Okay, so that's a gimme problem, but I'll find some other ones. So, where there's a will, there's a way. That's what I figure. It's not going to be that difficult. It'll be a little bit harder for me. It certainly will be harder for me. Okay? To, work around this problem of people wanting to farm out the problems, whether it's a hoax or not. So, let's have a look at the cubic spline voltage drop data, which is example 7.2 in your text. Okay. So I just want to see how you set up the splines. We talked a bit about how you mathematically set up a spline last time. You have the time X, the voltage drop Y, predicted voltage drop, for a certain model. I'm not sure exactly which one that was. I guess that was the actual cubic spline one. That's what I'm predicting. So this must be the cubic spline. And then over here, I'm predicting with just a single cubic. Okay? So there is a single cubic fit. Okay? Which doesn't seem adequate if you study the residuals. First they're low, then they're high, then they're low, then they're high again. Okay? So the pattern to the residuals. I didn't even write down the residuals because you can see it from this picture anyway. Right? And, well, actually I did write them down. Okay? High, low. Maybe it's not so obvious, but anyway, let's kind of have this loopy picture here. Okay? Cubic only model. So that's fitting the cubic polynomial to the data, which is reasonable. It kind of has a cubic fit. But this is the cubic spline with two continuous derivatives. That's amazingly good fit. Now, how did they figure out where to put the change points? Because when you do have a spline, there's points where you change it, right? In other words, what I have is one cubic, and then at this point I have a different cubic. And then another point, I have another cubic, okay, where the cubics are connecting to the whole curve is continuous. Moreover, it's second differentiable. In other words, there's actually a concavity to this curve. All right. So not only is so the first derivative is continuous, in fact. Okay. There's a second derivative. Now, how do you model twice continuously differentiable? Well, you drop. I think we talked about that last time. You take the model to be See, where is the model? See if it wrote it down somewhere. I don't know if I did it. Well, there are my regressors, but my actual model then is for the cubic spline with change points t equals 6.5 and t equals 13. I think it was. Yeah. There are 2 points. What would be the general one? The general cubic, where it would be something like beta 0, 0 plus beta 0, 1 x plus beta 0, 2 x squared plus beta 0, 3 x cubed plus beta 1, 0 x minus 6.5 plus to the 0 plus beta 1, 1 x minus 6.5 plus to the 1 power plus beta 1, 2 x minus 6.5 plus squared plus beta 1, 3 x minus 6.5 plus cubed plus, and then all the ones at the 13, which are like this one, only the index goes from 1 to 2. All right? So a whole bunch of parameters, what, 12 parameters, right, in this. Okay, so that was allowing for 1 cubic, all right, and then even a change in, and then even a discontinuity in a different cubic. So if we go back down to this picture here, so the general model over there allows 1 cubic here, okay, then at this change point, just any other cubic up to this point, just any other cubic whatever, okay, and then at this change point yet another cubic whatever. So there doesn't have to be any connection to the curves or anything, all right? And now in order to make it at least continuous, then we take off these terms, okay, to make it continuous. And actually, then to make the first derivative continuous, we take off this. And then actually I have a second derivative continuous in this problem I've taken off this. Okay, so I have a continuous second derivative. In other words, make it as smooth as you can possibly make it is what we've tried here. And if it didn't fit, then, for some reason, then that might be a bit odd. This is some kind of rocket thruster thing, and so there was some heuristic to actually make the change points at 6.5 and 13. So there has to be some heuristic. There should be. It doesn't have to be. There should be a heuristic in order to include the change points. If there's no heuristic at all, you might have to try to do some kind of nonlinear regression to estimate what the change points would be. We don't want to have to do that here. So this example is thrown in. There's a reason for this. Okay. In your computer repair time example for the exam, there was supposedly also a good reason for making the change point as it was. All right, so there you have this beautiful fit. Okay. So the only point about this example was to show you actually how to put in the X matrix or the columns. So you have X, X squared, X cubed. I need those for the first 3 parameters, right? The beta 0, 0 is an intercept. This will be my intercept. Therefore, my overall intercept. So I've gotten rid of all these other terms. Right? So I cancel these for continuity, cancel these for continuity of the first derivative, cancel these for continuity of the second derivative. It's simple, right? I argued that all last time. So I've got that. And so now you have how many parameters? 1, 2, 3, 4, 5, 6 parameters left in the model. Okay, one of them is an intercept. All right? So that just goes with the column once. So I don't have to code that in when I do Excel with the intercept, right? Because I'm using multiple regression. Excel puts in the column ones automatically. Okay, so here we have, so I have the X column, x squared, x cubed. I think x went from 0 to 20 by 1/2 minute. This was in minutes. X was in minutes, I believe. Or was it seconds? No, it was in seconds, I guess. Well, it's a time unit. I guess seconds. Because otherwise it's a long flight. Okay? For this rocket. Then I actually just put, how did I code the plus? Well, x minus 6.5 plus is 0 until you get to 6.5. And whether and sort of the change, as long as, if 6.5 is one of the values in its set, it doesn't really matter if it's, okay, x minus 6.5 is 0, okay? So it's 0 up until that, and then at 7 it changes to a plus. So then these are the pluses, and then I just cubed those pluses. So here it was 0.5 cubed, right? E20 minus 6.5 the quantity cubed, and here it was just 0. I just put it 0 by hand, so I didn't even use any if statements. I didn't, make any too complicated. Okay? So it's just zeros, and then these were zeros all the way down to 13, and then the same type of stuff. So it was actually the same numbers here, 0.1251 and 3.375 and so on. I hope that helps to see how it was. And so I just put in those, regressed on those 5 columns. All right? And those gave me the coefficients. And they were all significant. Okay. After the other. Each one after the others was significant. Remember, that's how these teeth statistics go. That if I had the full model, if I had the model with all these in here, but without the last cubic, okay, then that's not as good as with the cubic, because the cubic term is significant after those other ones. Okay, you get t statistics of 7.577, in other words, large F statistic, small p-value. Okay, so I can test whether beta 2, 3. So in other words, if I could test H2, 3, H0, beta 2, 3 equal to 0. I can do that with an F statistic or with a T statistic. All right, that would be, the F statistic would be SSR beta 2, 3 after all the others, beta 0, 0, beta 0, 1, beta 0, 2, beta 0, 3, and beta 1, 3. Okay, that would be the notation for the numerator degrees of freedom, and then divided by 1, because there's only one beta here. Okay, divided by MS res for the full.
MS res including beta 2, 3, right?
Yeah, for the full model. Okay? MS res for the full model, so that would be 0.717. Okay? So what is this business? Well, that turns out just to be the square of the 7.5774. Okay? I don't have, in other words, what I normally have to do in order to calculate this is look at the regression sum of squares for the full model, which was 260.18. And I'd have to subtract off the regression sum of, or subtract that from the regression sum of squares from the reduced model, where the last term was not put on there. All right? And so this comes out to be the 7.5774 squared divided by 0.0717. Okay. I'm sorry, that's the wrong.
No, because that's just the F itself should be your 7.577.
I'm sorry, that's correct. Right? That's correct. Yes, I'm sorry. So this should be something so that divided by 0.0 you get 7.5. So whatever this is, it's equal to, yeah, that's correct. That's correct. So we should check that. What is this number? Okay? And does everybody know how to calculate? In other words, okay. This is the t squared. equals t squared. The F statistic is a t squared. That is correct. The F statistic is a t squared. And so how do I actually get that? I'd actually do another computation in order to find this change in the regression sum of squares. How much of the total sum of squares was accounted for by the regression? Regression accounted for 260.18 out of the 262.69 possible total sum of squares corrected for the mean. Okay? Which is a high R squared. Up in the 98, 99% range, right? So most of the sum of squares were accounted for. It's a great fit. All right? Now, but how much of the sum of squares was accounted for by the model where I didn't include this last cubic term? I only included the one change point. Okay.
Should we do it?
Okay, sure. So let's do it. Let's double check. So let's just go ahead and regress.
Is that the denominator that is?
MS-res. MS-res. Yeah. Oh, I got add-ins on this one again? Thought I already fixed this one. Okay. Okay, input Y range, voltage drop. Here it is. Input X range. Let's put all of these, but not the last one, right? Okay, labels, residuals we don't really need. I'm just going to skip that. Okay, output range. Let's put it somewhere where it's not going to cover everything else. Okay, down here. Okay, so that gives us now SS res is 256.06. Okay, so this is the 260.2 I had before with the 260.2 minus the 256.06. 260.18 it was. Okay, over 0.0717.
So that's not B23 regressed on that, it's Y regressed on everything except for B23.
Right. Yeah. It's how much the either SS res or SSR changes by, because they're equivalent. Just you have to, one has, it's the bigger number minus the smaller number. So you can see that the SS res changed from 2.5 up to 6.62. All right. That's a big percentage change, but it's not numerically. It's not a big change. Okay, because you can see the regression sum of squares changed from 256 up to 260. All right, that's not that big of a change out of the total sum of squares. But because the error sum of squares is so small, okay, to the full model, then you get this ratio. So it's 4 divided by 0.07. 13 times 4 is about 52, which is about what this is. Okay, 52, 53, 54. It's the F statistic. They don't report the F statistic here. They only give you the T statistic, 7.5774. Okay? So it's somewhere above 50. Between 50 and 60. Okay? Comments about this? So that's actually the hypothesis you're testing. You're testing beta 2, 3 equal to 0 with that T statistic. And what you're doing is you're really trying to see what the fit is like with that term, without that term. Okay? That's the self. Okay. Versus without that term. All right. I won't draw the picture for that. Questions about this? This cubic spline model is just showing you how to code the variables and sort of recalling how it worked. That's all there really was to it. Now, that said, you could solve your problem on the homework with an intercept if you wanted. Okay? You can set it up that way. So I think I was trying to get you to do it without the intercept, okay, by putting in the columns of x accordingly. But here, so there's different ways of doing it, okay, getting the fit. Okay. All right. Let's have a look at another polynomial model. That's the chemical process conversion. This was just a case where the author has, in table 7.7, given you some data. Central composite design for a chemical process example. What they're looking at is a percent of conversion is the y variable. Y is the percent of conversion of whatever you're trying to make. Okay? Okay, so from 43% to 81% conversion in this data. And you've got x1 is a coded temperature, x2 is a coded concentration. And then what I've done is and then I put in x1 squared, x2 squared, and x1, x2 for a full quadratic model. The values x were coded, all right, such that each of the pairs, minus 1, 1, 1, minus 1, minus 1, minus 1, 1, 1, 1, minus 1.414, 0, minus 1.4142, and 0, and so on. Each of those, except for the centers, which was 0, 0, 0, 0, 0, 0, and 0, 0, were at distance square root of 2 from the origin in the x1, x2 plane. So that was called the central composite design for this particular model. So what they did was they took the x1 and x2 plane, and they just the minus, they've coded the temperature and the concentration by linear transformations. Okay? So let's see, what was it? In the original data, the kit told you the temperature was 200 degrees or 225 degrees or 189.65 degrees or 260.35 degrees, corresponding to x1 is minus 1 is 200, plus 1, I'm sorry, it could have been 250, plus 1 at 250. So it's 25 degrees per unit change in the coded variable, right? So they had to actually, they actually had to put those temperatures in. They had to design those temperatures in this problem. Okay? They want the central composite design. So they had x1 and x2, and they took, these 4 points, and then you also had, I'm sorry, did you have those 4 points? Yeah, 1, minus 1, 1, minus 1, minus 1, 1, minus 1, minus 1, 1, and 1, 1. Those are the 4 points of the square.
And then you get the...
Then you have these points on the axes, right?
They just have to fill out the circle.
There's 4 points on the axis to get here. Okay, so then you have, this circle here going on. Okay, and then you have 4 points in the middle. Okay. Is that right? They repeated 0, 0 4 times. They showed this picture in the actual original units. Okay? In the book, page 245. Okay. The reason for doing that is it turns out then the prediction the variance of the prediction is going to be the same at each of these points. Okay? It turns out. All right? I'm not going to get into that. That's probably a nice computation, but I think I won't get into it. Okay?
Assuming that a linear model is appropriate.
Assuming that this model is assuming that the model fits. Yeah. Full quadratic model. Okay. So yeah, I believe that is assuming that the full quadratic model. Let's just double check that for you, Shane. It says yeah, I'm not sure if you need all the quadratic terms or not, whether it would actually depend on whether you put those quadratic terms in or not. I'm not absolutely certain about that. I'll have to check that. Okay? The author did not say about that. And I'm not certain. Okay. In many response service problems, the experimenter is interested in predicting the response y or estimating the mean response at a particular point in the process variable space. The response surface plots give a graphical display of these quantities. Typically, the variance of the prediction is also of interest because this is a direct measure of the likely error associated with the point estimate produced by the model. Recall that the variance of the estimate of the mean response at the point x0 is given by variance y hat at x0 is equal to x0 prime, x prime x inverse x0, okay, with the sigma squared in here. Okay, where x0 prime really is a row out of the x matrix. Okay, this is a row out of the x0 row out of the x matrix. So that's the variance, and with the central composite design, they make that the same for each. They make that the variance the same for each of these points on this circle. Okay. And I'm assuming that that is true no matter whether the x matrix is the full quadratic or just the linear. But here we have to assume that it means the full quadratic. But I'm not sure, since he didn't actually prove that this is constant, you would have to see about that, right? Okay, so what's the actual, he didn't actually show that in the appendix either, so that would be a good extra credit problem to actually see whether that is a constant or not in this problem. He did actually compute x prime x inverse in this, well, he calculated x prime x. He did not calculate x prime x inverse. X prime x is not quite diagonal. It has some off diagonal terms. So it's not completely obvious how that would work out. Okay. All right. So here, that's called the full quadratic model, where you put in all possible linears and quadratic terms in two variables. Okay, you have x1 and x2. You have x1 squared, x2 squared, and x1, x2. Now, how would you test the hypothesis that none of the quadratic terms are necessary, that all the quadratic coefficients are equal to 0? Hypothesis that beta 1, 1 equals beta 2, 2 equals beta 1, 2 equal to 0. How do you test that hypothesis?
Same way we did it excluding one model, except for now we have to redo our thing excluding all three terms.
Yeah, you exclude all three terms. So you're not going to get the answer from
the t value.
You're not going to get the answer from the t squared, right? You have to use the extra sum of squares method. So here are the t values for whether these individual terms are important after the other ones have been fit. None of them are, well, yes, they are. They're all important after the other ones have been fit, apparently. So you could guess from that all three of them together certainly are going to be important. So it's trivial that all three of them together would be important. Well, let's say they weren't all so obvious. Okay, let's say they were all kind of small t-statistics, like all 1.5. Then you want to know if all told you had a significant contribution to the model from the total mass of the quadratic terms. See what I'm saying? Pretend that all these p-values were something like 0.2. Okay. Then you'd want to know whether these three quadratic terms together gave you some significant fit, improvement in the fit, significant improvement in the fit. So you can test this. So you have to calculate SSR, beta 1, beta 2, beta 1, 2 after beta 0, beta 1, and beta 2. Okay? And then it has 3 degrees of freedom because there's 3 betas in there. So the F would be this divided by MS res for the full model again. Okay, so we've done that over here, I believe. Because what I did is I took, then I regressed only on the 2 regressors, x1 and x2. So I took the reduced model and I found the SSR. The SSR is 914.4 for the reduced model. So it's only explaining 914 out of the 1768 total sum of squares. Whereas when I put in the full quadratic model, almost all of the total sum of squares are accounted for, 1733. Okay, so if I want to test the influence of the quadratic terms, I test the hypothesis all the betas with double indices are equal to 0. Okay. 3 degrees of freedom, SSH. How did I calculate it? It was the difference of those two, the 1700 and something minus the 900 and something. That was 819. It says C29 minus L29. Here's my L29 right there. Oh, I actually subtracted the SS reses, which is equivalent to subtracting SSRs, except that I had to switch it, the order, right? Okay, 854 was the residual sum of squares for the reduced model. Okay, I get a smaller residual sum of squares, only 35. That's in C2. I did subtract the SSRs. I got my rows wrong. Anyway, it was the 1733 minus the 914. That gave me the 819, whatever. Okay. But you see, it's the same as if I subtracted 854 minus 35. That still gives you the 819. Just subtracted in the reverse order. Okay. How did I calculate my FH? I took this number, 819, divided it by 3, then divided by MS res for the full model. So I had to go back over here and pick up my MS res for the full model, which was 5.89. So does that make sense? 819 divided by 3, that's about 270 divided by 5. Okay, and a half. It gives you about 45 or 50. Make sense? So that's my hypothesis. It has 3 and 6 numerator and denominator degrees of freedom because MS res had 6 degrees of freedom over here. There it is. You can just read it from the table. Of course, you should know how to calculate that. How many parameters did I have? I had a total of 1, 2, 3, 4, 5, 6 parameters. And how many observations did I have? Well, you could count them here. There were
9 plus another 3 to get 4 in the middle, right?
Yeah. So there was 12 observations. So 12 minus the 6 parameters is 6 degrees of freedom for the residual sum of squares. So going over some of these theories, make sure you know how to, how many degrees of freedom and so on. Those are some of the things I could ask you.
I'll just say, oh, here is the data. Suppose the analysis of variance table, a piece of the analysis of variance table come out like this. Fill in the rest of it. Okay? Whatever. Give me the F statistic. You know, that kind of stuff. Little puzzles. That's a possibility. Okay, so there's how you could do that. And I actually did calculate HIIs and all that stuff. Did everybody get the email, get the information that you can easily get the diagonal of the matrix out? How did I get this? HII. Here is the formula. It's kind of long. It says, do the following multiplication. What is the multiplication I'm going to do? I'm going to take, what I'm going to do is I'm going to get a matrix, a square matrix. The operation that does it is this. I'm going to get a matrix H11 down to HNN and all zeros here. That's the first, what the first factor in the multiplication is. And there's only one M mult in this formula, right? It's one M mult. And then it's going to multiply that by a column of ones, and it's going to give me the column H11 down to HNN. Okay? That's how I get the HIIs. That's the formula that's in that. What does it say? It says take the column of H, which is just a row vector of ones. Excuse me, that's not a row vector of ones. It's actually the actual numbers of the columns. Like here it would be, if it's Q, I think it's, I don't know, what position is Q in the alphabet? M is 13, N, 14, 15, 16, 17. So it's like 17, 18, 19. Those are the column numbers of H. It all depends on where it is. Okay? So this would be, I think the column of H is a vector 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. And so on. Keep going. Because I think, well, no, that was as big as H was. Okay? So, right? That's what the column of H is, a row vector. So if you're looking right here, it's this column of H. Let's see if I can point at it. Way in here, this column of H business. Okay, that's actually a row vector. You could test that. All right, by writing it down somewhere. H, I had to refer to this, so I actually made a reference for this matrix. I called it H in the reference bar. So then I take the transpose of that. It'll give me a column vector of some numbers. And I just raise it to the 0th power, and that gives me all ones. Okay. So that was this cute thing. That's the 1, 1, 1, 1, 1, 1, 1. Okay? If you put in row of H, you would think, well, that should give you wouldn't have to use a transpose, but it turns out row of H is also a row vector. That's the default in Excel. I don't know why. Okay. So you still have to use the transpose. So I think you could replace the column by row. That would do change the number of typing units by 4. But I just left it because I didn't want to play with this formula anymore. Okay? Now, what about the before that? What's going on there? It says row of H minus the min row of H equals the column of H minus the min column of H, star H.
Gives you the position in the matrix.
Yeah. It says that the row has to be equal to the column relative to where the row started and the column started, because the row of H is a number referring to where the actual thing is in the sheet. All right, and the column is simply just some number. You have to use the min row and the min column. Okay, to basically get in the abstract, it says that the I should equal the J. And then in this star operation, I don't actually know what it is. But it's pretty clear what it does. It takes the whole matrix and says if the row is equal to the column, then you put that in, and otherwise you put zeros. Okay? I never heard of it before. Certainly it wasn't easy to look up. But somebody knew that star operation. So then you're just getting this diagonal matrix. And you multiply it by the column of ones, you're getting the column of H's. So that's the trick. Then put it in the array formula. Okay. So I have to specify a column. So I actually had to highlight this whole column, right? Highlight this whole column first, and then put in the array formula there. Okay? And then hit Control, Shift, Enter. Okay? To get it to fill in. Of course, it was an easy one in this case, so it wasn't all that important to do, but H's were all easy. So there's the column of H's.
Which now you look at those and you say, oh, all those SI squares are actually pretty close. And you don't.
So you don't have, you have high influence presumably at all of these points around the circle, but none of our students are big, so they don't, they'll have equal influence, okay? But they're all pretty high in this example, you would think, because the HIIs are all pretty big. Those are all, according to the cutoff for what HII should be, which is 2p over n. What is 2p over n in this case? Actually, no, 2p over n in this case is 1. So I guess they don't have high influence. Okay, 2p over n is 1. Though the author said you have to be a little bit concerned about that when 2p over n is bigger than 1. Of course, you can't have HIIs bigger than that, because the HIIs are all less than or equal to 1. But you'd sort of think that all these points on the circle all could potentially have high influence, but they all have leverage on the outcome, but none of them have high influence. Okay. But none of those points exceed the cutoff, which is 1 here, because the sample size is kind of small. Okay. Any other comments about this example? I think it was mostly just say, well, there's a quadratic fit. It's a multiple regression model. There's not that much to say about it, except if we were going to get into the design of experiments, we talk a little bit more about this central composite design.
Would this be a good time to take a break?
Okay. Let's take a break.